Good. Okay. Sorry.
Thanks. Sorry for the technical.
All right. Let's take it away. Thank you.
Okay. Thanks. I'm Yanglin Hu, and today I'm going to talk or work on the feasibility of detecting quantum delocalized effects on gravitational redshifts in optical lattice flow. This is joint work with Maximilian Rock and Misha Wu. And Misha and I were in ETH then when we do this work, and now I'm in National University of Singapore, and Misha is now in area of Grenoble, and Max is still in Vienna. Yeah, so last speaker just mentioned that there is another experiment in Gila, right? Yes, we are aware of that experiment, and our setup is kind of different from their setup, but we are open to discuss both ours and theirs and the similarities and differences between them. Yes. So till now we have several different quantum gravitational theory has been proposed, and in order to test those of quantum gravity theories, a bunch of experiments on quantum gravity has been proposed. That includes this one. This is proposed by Mueller and his colleague. This discuss to detect quantum gravitational redshift with atom interferometry. And we also have some, and later on, Dr. Zhang, she is also here. She developed here, as well as Professor Ufrich, he also developed a similar idea. And later on, both also proposed an idea that quantum gravity can entangle to far apart atoms, and that entanglement can be witnessed by a Bell measurement. And we also have some other works by Kumar and his colleague to discuss if there is some, if there has been some modification to the quantum canonical commutation relations, then this this modification could be possibly detected by some tabletop quantum oscillators. And recently, another work by my colleagues and Kandelwa, they proposed that there could potentially be a discrepancy between some quantum gravitational redshift between the quantum superposition and the classical mixture. This discrepancy could possibly be detected, and in their work they consider that suppose we have a point-like quantum clock that which is free falling, and it has an inner degree of freedom which is used for timing, and a kinematic degree of freedom. And so by extending this the relativistic Hamiltonian of this quantum clock, we can obtain a Hamiltonian which is of this form. In this form, there is a term which there is an interaction term which couples the inner degree of freedom for timing and the kinematic degree of freedom. And this term will lead to the gravitational redshift, or the time dilation of this quantum clock. And if the kinematic degree of freedom of this particle is in a Gaussian state, then the time dilation from this interaction, it will be exactly the same as the time dilation predicted by the proper time in the classical theory. However, if we consider that the kinematic degree of freedom is either in a quantum superposition of two Gaussian states or in a classical mixture of two Gaussian states, these two Gaussian states, they have a displacement of delta x, and the standard deviation of these two Gaussian packages are sigma, and they have a momentum p, and the probability to have one state is lambda, and the probability to have another state is 1 minus lambda. And in this case, if we start with the quantum superposition of these two states, we can get a time dilation, which is we denote by T superposition. And if we start with the classical mixture, then we get a time dilation, which is denoted by T mixture, and their difference we denote by T covariance. We regard this as this frequency between the quantum of the time dilation between the quantum superposition and the classical mixture. And from their previous paper, they show that the scale of this frequency is 10 to the minus 16 seconds for 1 second of measuring time. And on the contrary, the scale of relative accuracy for the state of art atomic clock is 10 to the minus 18. That indicates this discrepancy is possibly detectable by the state of art atomic clock. Yes. But there are still some remaining questions. One problem is that the state of art atomic clocks are usually confined. For example, the optical lattice clock or the iron trap clock. But in their work, the situation they discuss is to use a free-falling atomic clock, which usually has a lower accuracy than the confined clocks, right? And then some questions arise whether we can turn their previous protocol into some protocol with confined clock. In that case, is the discrepancy still there, and will the noise do any harm to this discrepancy? So in this work, we try to answer these questions. We first investigate the discrepancy between the quantum case and the classical mixture case in a confined atomic clock model. And our results shows that the discrepancy remains there, and it seems that it's detectable. And we also try to propose a more realistic experimental protocol which use confined atomic clocks to detect the discrepancy of the quantum superposition and the classical mixture. Okay. And we finally also analyze for some possible noise. For example, we analyze the amplitude and phase damping noise, and also some diffusion noise. We analyze under this noise whether the discrepancy is robust. Yes. And we also give some regions on the noise parameter in which we can still see the discrepancy. Okay. Now we start with our theoretical model. So we adapt the model from Dr. Sykes' PhD thesis, and we consider a point-like atom clock that evolves in a curved space, and we try to write, that atomic clock has an inner degree of freedom, which we denote by C, and kinematic degree of freedom, which we denote by K. And this atomic clock evolves in a gravitational field, and we write down the Hamiltonian in the lab frame, which is as shown there, and we consider a static metric, and we also assume that the the gravity is weak enough such that we can use the post-Newtonian approximation. And in that case, these parameters are written as below. And as the next step, we extend the Hamiltonian in the low velocity and flat space limit. And we also make the replacement, we're replacing the mc squared by mc squared plus hc. That means we split the Hamiltonian into two parts. One is the clock Hamiltonian for the inner degree of freedom, and the other part is the kinematic, is the Hamiltonian for the kinematic degree of freedom. And we also consider that the atomic clock it is subject to some potential, which is this U in this laboratory frame. And doing these two replacements, we can get the Hamiltonian in the approximation for the Hamiltonian in the laboratory frame. We see that this Hamiltonian contains two parts. One is the part in the red sphere. The red is not it's not as red as I have on my slides. So we have the right part. That part it has the Hamiltonian for the inner degree of freedom and the kinematic degree of freedom respectively. And we also have the terms in the blue part. That blue part is a Hamiltonian that couples the inner degree of freedom and the kinematic degree of freedom. Yes, and all the terms are listed as below. And we have to remind you that we do not we keep all the terms that is written explicitly here, and also some terms we do not written explicitly here. Those terms are the terms that in the original Hamiltonian is below the order of c to the minus 6. We keep all the terms and pack them in the terms that is c to the minus in the terms that contain in O c to the minus 2 terms. Right. So, but later we will show that all those terms can be dropped safely when we discuss both the discrepancy and the variance of the discrepancy. Yes. So. Okay. Now we discuss how we compute the evolution of the system. We use the perturbation theory to compute the evolution of the system. We treat the HC and HK part as the unperturbed Hamiltonian, and we treat the interaction term that couples the inner and kinematic degree of freedom as the perturbative Hamiltonian. And we can write down, we also assume that the decoherence via the kinematic degree of freedom is very small. This is it's much small. It is much larger than the decoherence of the inner degree of freedom. This is because the inner degree of freedom they are usually using some transitions with very narrow line width, and so we make the assumption. And we can write down the Lindblad equation, which is as follows. And this FC and FK terms, they are used for the time evolution, the inner degree of freedom and the kinematic degree of freedom. And we use this F interaction to denote the interaction between the inner, to denote the time evolution for the interaction for the interaction between the inner and kinematic degree of freedom. Okay, and then we can again expand the. We consider that the initial state of the clock is disentangled between the inner degree and the kinematic degree of freedom, and we can use we can expand the density matrix of the whole atomic clock and expand it order by order. And here we only write the first three order. Here this real knot, it consists of all the terms that deviates from the unperturbed evolution by at most c to the order of 0. And this rho 1 corresponds to all the terms for c to the minus for the order of c to the minus 2, and this rho 2 denotes all the terms that corresponds to the order of c to the minus 4, and etc. And we do not elaborate to write more equations. And in this way, we get the time evolution for the inner and kinematic degree of the atomic clock. Okay. And now we use the above atomic clock to consider this frequency standard. And for atomic clock, the Hamiltonian of the inner degree of freedom is simply a two-level system Hamiltonian. And this atomic clock, it is used to compare the transition frequency omega 0 with some very stable laser, and then this atomic clock uses the very stable laser to generate the time signal, right? And the comparison between this transition frequency omega 0 and the laser frequency is usually realized by this Ramsey experiment. So this Ramsey experiment, it will first prepare the atom in the plus state with pi half cos of the laser, and then we wait for some time t, and then we measure in the plus minus spaces with another pi half cos of the laser, and then we will get some fringes, Ramsey fringes, which is shown on the right. And from the fringe, we can get the center of the fringe, which is omega tilde. That is, and we can get the contrast of the fringe, which is denoted by p tilde. And when the clock is moving in a flat space, when the clock remains still and in a flat space, the center of the fringe is just the transition frequency omega 0, and the contrast of the fringe will tell you how accurate you have for the center of fringe. Okay. Now we consider that the atom is moving in a gravitational field, and the relativistic effect will change the center of fringe, and also will change the contrast of the fringe. Actually, it will shift the center of fringe by this I1 times omega 0, where I1 is some parameter we derived from the perturbation, and also the relativistic effect will decrease the contrast p tilde a little bit, and this decrease is also given by by the perturbation theory by I2 and I1. And here, only in this stage we can say that we can safely ignore all the c to the minus 2 terms in this vk and also wk. So that's where we ignore all the high order terms. Okay. And now we consider the discrepancy between the quantum superposition and the classical mixture. Consider that we have two atomic clock. One prepare its initial state with and the kinematic degree of freedom is prepared in the superposition of these two Gaussian states. And another atomic clock, it prepares the kinematic degree of freedom in this classical mixture of two Gaussian states. And then we perform the Ramsey experiment. And in the end, their center of fringes will result in a discrepancy in the center of fringes between two cases. And the discrepancy of between the two cases is shown here by omega tilde zero coherence, and it is related to the parameter we derived from before from the perturbation theory, and also it's the variance on this center of fringes will also be enlarged a little bit, and the increase will be described by this delta 2. Okay. Now we consider how do we realize the previous mentioned protocol with some real experiments in confined atomic clock. For example, the optical lattice clock. We use the example of optical lattice clock because the optical lattice clock usually now achieves the highest accuracy among all the atomic clocks. Okay. So the atomic lattice clock is based on the optical potential. This optical potential is a state-dependent potential, and so for different electronic states, they have different. They will feel different they will feel different optical potential. So for this, for the optical potential filled by the electronic state n, it is described by this alpha n omega p, which is the polarizability of this state n, and under the laser with frequency omega and polarization t, and it's also proportional to the square of the electric field of the laser. Yes. So this is the optical field, and so when we use standing wave to generate the optical field, we will get the optical lattice. So usually the optical lattice is aligned parallel to the gravity in order to reduce the hop between, in order to decrease the hopping between different sites, in order to increase the accuracy. And usually the optical lattice is also made very deep, so that you can apply the harmonic oscillator approximation. That is, we extend the optical field near to its balanced point. Yes, so this is the optical lattice, and we also consider optical lattice because it is also convenient to use the optical lattice to prepare the quantum superposition. That is, we can also we can also apply the technique of state-dependent optical lattice. So we consider the case in which the polarizability of the ground state subject to laser with frequency omega and polarization sigma plus is larger than that of the polarizability of the excited state, but the polarizability of this ground state subject to the laser with omega, and polarizability with sigma minus is smaller than that of the polarizability of the excited state subject to the laser with polarization sigma minus, then we can apply the optical. We can apply the state-dependent optical lattice with two standing waves with different polarization, as is shown on the right-hand side. So we use this technique to prepare the superposition and the mixture. Okay. Now we give our setup of our protocol. We require that the atom we use, it has an energy structure like this. Here we have two stable states and two metastable states, and two unstable states, and and the width of the line, it represents the transition of the transition strength of the line, and we also use the color to represent the wavelength of the transition. Okay. So we require the system initially to be prepared to involve the stable state S1, and then we use a transition to transit this stable state to one of the metastable state, and then we apply the Raman transition between the two metastable states to prepare superposition of them, and then we apply the state-dependent optical lattice to entangle the electronic state and their kinematic state. And then, if we want a quantum superposition in the kinematic degree of freedom at last, we will apply a Raman transition between the two metastable states to get this state, and then we transmit one of the metastable state to the unstable state, and then from that state it's spontaneously decay to the ground stable state, and in that case it will result in superposition in the kinematic degree of freedom. Okay, and for the other state we can use some technique called electron shelving to abandon it. The electron shelving, it is you induce a transition between that metastable state and unstable state, and the atom is transferred to the unstable state, and from the unstable state it falls quickly back to the metastable state, and by repeating it, it gets enough momentum to get burst out of the lattice. Yes. So if you want the kinematic mixture state, so you first transist one of the metastable state to the unstable state and get S1 R1, and then you transit the other metastable state to the unstable state and wait for spontaneous emission, and you get S1 minus R, and this results in a spatial mixture of the two states. Okay. So this is the scheme that you get the final state. So because the time is limited, I only put it here. All the procedures are described as before, and we go to the next. And we consider whether or protocol can be applied in this Magnesium atom. Our answer is yes. We can find corresponding states, and we do not elaborate it here because we limited time. Okay. So we make some we did some numerics to compute the discrepancy and also the delta 2 square for the magnesium 24 plot. And our results show that the discrepancy between the quantum superposition and classical mixture it reaches 10 to the minus 19, which looks promising. And at the same time, the variance does not increase very much for some certain ranges. So we conclude that it looks good to detect this discrepancy. And we also consider amplitude damping and phase damping and diffusion and the kinematic degree of freedom. So we show that for the amplitude damping, which is on the x-axis, and this diagram, this figure is for the discrepancy. We show that by increasing the amplitude damping decay rate, the discrepancy decreases, but as long as this decay rate is smaller than 1%, it's fine. And phase damping doesn't do any harm. And for the diffusion, it will increase the variance, but as long as the diffusion rate is smaller than 1%, it's also fine. So as a conclusion, we think it's feasible to conduct such an experiment, and we mainly look on magnesium plot, and it has the discrepancy is large enough, and the variance it doesn't increase a lot. So that's all. Thank you.
Sure, yeah.
One quick question if there's... Yanglin?
Yeah, I just didn't want to take
Want
that.
to go take the microphone?
Okay, we have a lot of shared interest. I really enjoyed listening to your talk. Something I didn't quite understand from this scheme, maybe you can quickly clarify. I thought you would be talking about superposition of internal clock states M and the center of mass state, but in the scheme I thought we end up with the S1 state and the superposition of alphas. So just maybe you can quickly clarify how you intend. Yeah.
Yes. So the point is that so here, so in this stage, because you will of course you will have some other state on this state, right? Then you use the electron shelving to totally abandon that state. The electron shelving, you can think it as some measurement on that state, and with that measurement, you also give it enough momentum for the atoms on that metastable state, and it will give the atom enough energy to let it run out of the optical lattice, such that you can clear the atoms in that state with electron shelving, and then you result in this the superposition of the kinematic degree of freedom, but you don't get the superposition on the internal states. That's fine. Is that clear?
So that the superposition on the internal state you would create later with the usual Ramsey scheme as you described.
Pardon?
Okay, maybe we can take this off the line.
That sounds like paper discussion. Okay, let's thank the speaker again.